is a pretty typical method of joint problem. Basically, you've got some goofy looking truss that you've never seen in the real world, and it's like, find the blah 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 forces, and it usually asks you to find the reaction forces as well. And you're like, okay, and then you work it out, and it's a bunch of algebra. And then you think, wow, wouldn't it be amazing if I could do this in SolidWorks? Because I'll bet it'll happen a lot faster. And the answer would be yes. So we're going to solve this by hand, and then we're going to do it in SolidWorks. We're going to solve it by hand to make sure we actually get the right answer whenever we do it in SolidWorks. So I'm going to actually make this a little bit bigger so that you can see what's going on. Okay. Now, as always, it's a good idea to start by plugging in little distances and values and stuff like that. So this is a 45, 45. So, well, this big one right here is actually a 45 as well, because it's 4, 4. So I'm just going to start labeling sides. So I've got a 4 square root of 2 along this whole distance here, and since this angle here is 45, I can guess that this angle is also 45, making the other side also 4 square root of 2, and this is 45 and 45, which is nice. Let's see, we've got a 45, 45 here, so if that side's 4, then the two little sides are also 2 square root of 2. I don't know why I'm switching colors. 2 square root of 2, amazing. This is 60 degrees because we have an equilateral triangle here, so since that's 60 and that's 90, let's see. I think we can safely say that this is going 60, 60, 60. So here's 60 to here. Because it's straight, it has to do with the fact that this is straight, so that makes that 30, so that has to be 60. And then this guy up here is 30, so we have a 30, 60, 90, so 4, 8, and 4 square root of 3. And I think we have enough distances to go ahead and do some basic stuff. Oh, we can go ahead and label in our reaction forces. This is a roller joint, so that's A in the Y direction. This is a pin joint. So we can throw this E in the Y direction and E in the X direction. Yay! Some of the moments about E. So if I sum the moment about E, this guy here goes to be a negative moment. So he's negative 200 and he's 4 away. And then we have this guy here does a positive moment. So he's 300. How far away is he? He's a distance of, oh, I have that distance. I don't have this distance. Okay. I can do that. So this right here would be a triangle, and this would be 60 again. So this is 30 again. So if that's 4, then that makes that 2, so the whole distance is 10. Okay, 300 times 10. And erase all this junk because it's going to confuse me later. And then, let's see, this guy here does a negative moment, minus AY. And he is, oh, I didn't do this one. So 4 square root of 2, 4 square root of 2. If I look at this triangle, that means the guy down here is 8 square root of 2. No, not 8 square root of 2, just 8. 8. Okay, so negative moment, and he's 8 away. So I've got 8 AY is equal to something 2200. So AY is equal to 275. Yay, math. Okay. And then I can sum the forces of the whole system. So again, what I'm looking at is this whole giant system. Because I can do that, because static says that I can look at the entire thing or I can look at parts of things. So I'm going to look at the entire thing. So there we go. And some of the forces in the x direction are just, let's see, E sub x and 200. So that means E sub x is negative 200. Beautiful. And then I have the sum of the forces in the y direction. The sum of the forces in the y are AY, EY, and minus 300, that has to equal 0. So I have that EY is equal to 300 minus AY, or 25. Good? Good. And we're just assuming all these are in meters and newtons because units are for children and engineers and people who actually want to know things and not just students just desperately trying to understand. I shouldn't say that. You really should pay attention to your units. We're going to pretend that everything was already labeled. I did label the newtons, I just didn't label the meters. We'll pretend I did that. So EY is, let's do EX, negative 200, and EY is positive 25. Newtons, newtons, and I'm going to save this for later because I have a feeling I'm going to need to know what these guys are. So the next step is going to be to actually start analyzing the individual joints in the system. So in order to do that, I'm going to move all of this around so that I have a nice pretty workspace. Okay, there we go. All right, so let's start examining individual joints. It doesn't really matter where we start, it just matters that we start somewhere that doesn't have more than 2 unknowns. So if I wanted to, I could go ahead and I could start here. So if I look at the joint B, okay, if I look at joint B looks like this, and she's got 300 going down here, and she's got some other tensions. So there's a tension going straight off, and that's tension BC. And then she has another tension going off this direction, and that's going to be tension BG. Okay, this is a 30-degree angle, and that's good. Because I can break that out, so in the 30 direction, across from the 30 is the 1/2, so this is going to be tension BG over 1/2, and the component going in this direction is going to be tension BG times the square root of 3 over 2. So if you're wondering where that came from, we're just going to be doing this a lot, so kind of good to get used to it. So this is not a very good picture. So I have tension BG, and I have a 30-degree angle here. So I know that the opposite is the sine of 30, and the sine of 30 is 1/2, so that's 1/2 tension BG. And the adjacent is the cosine of 30, so that's square root of 3 over 2 tension BG. And because forces move around, I can move this guy over here. So the 1/2, why did I say divided by 1/2? Maybe that's why you're confused. It's supposed to be times 1/2. I was trying to say divided by 2. I don't even know what I said. I might have said the right thing and written the wrong thing. But anyway, that's how the tension BG gets broken out. So I can actually remove tension BG because it's no longer there and it's just replaced by its components. Okay, so then I can do the sum of the forces in the, if I do the y direction, that's the least number of unknowns. I have 300 going down. I have 1/2 tension BG going down. So 1/2 tension BG, and then I'm just going to do math. So tension BG is 600. Seems decent. I like it. I'll take it. All right, then I can do the sum of the forces in the x direction. And those are, let's see, they're both positive, tension BC and tension BG times the square root of 3 over 2. So that equals 0. And I'm going to do more math and get negative root 3 over 2 times tension BG, which is also negative. So I've got, what is that, 300 square root of 3? So I can also say that that is 520-ish. There we go. So I have 2 more to add to my lovely list. So I now know that the tension of BG. Now I've drawn everything initially in tension. So if I get a negative number, then that must mean that it's in compression. Because if I have the line going out, then the joint is in tension. So since I got a negative number, that means that the joint is actually in compression on that side. And then B to C is 520. He's positive, so that one's actually in tension. Because it means I guessed right. All right, and these guys can come over here and join the fun. All right, and I'm just going to do this like 800 more times, and it'll be amazing. And you'll be so excited because I have no idea. Because you're watching this video, and you must be watching it on purpose because you want to learn things, and you'll learn stuff, and it'll be amazing. You'll be like, yay, I learned stuff. All right, so I'm going to start setting this guy up. So at joint C, I have joint C like this, and off to the left is this tension BC, which I already know is 520. So 520 this way. Then I've got this one and this one. And these are both 30 off to the center. So that means that they're, so I have TCG and TCD. That means that the opposites is 1/2 of that, so I'm just going to kind of draw in yucky, TCG. So this way is 1/2 TCG, This one is 1/2 TCD. This direction is root 3 over 2 TCD. Now this guy is all taken care of, and this guy is root 3 over 2 TCG, like that. And then these guys can go away. So I've got all those different little components of those forces going through. I'll get rid of the ones in it. Alrighty. So now if I want to do the sum of the forces in any direction, I'm still going to have two unknowns. So sum of the forces in the x, I have negative 1/2 of that, and then plus 1/2 of the other one, and minus 520 is equal to 0. And the sum of the forces in the y tell me that minus root 3 over 2 TCG and minus root 3 over 2 TCD equals 0. And if I do the math, I get that TCG is equal to about that negative 520 again, which makes sense. And then I get that TCD is equal to 520. There we go. So I've got these two, and that's just because I did math off to the side, so you don't have to watch me do math, you just have to watch me do physics. And what would you rather watch me do, math or physics? It's up to you. There's other videos that you can just watch me do math. So in this video, I'll just make you watch me do physics. And I decided to stop labeling units again because, I don't know, because I'm lazy. Alright, so now I don't need any of this anymore. I'll just make you tiny and then leave you. Because I only marginally think I'm ever going to care again how I got those answers, because I'm pretty sure they're right. Okay. Now we're going to keep doing this over and over and over and over and over and over and over again. Now one of the things that's going to happen is we're going to come over here. Let's say we're next going to approach joint D. So now we're going to look at joint D. Now hopefully as you've taken a look at this, you might recognize that right here we've actually got a zero force member. And it's a zero force member because it's intersecting something else, and there's no external forces on that joint. So that means that the guy that's coming in off to the, that's interrupting the straight line, that has to be a zero force member. And the nice news about that is it actually allows us to, I lost my little F. But that allows us to make a much more simplified free body diagram for joint D. So again, set up joint D. And if you kind of get the gist of what you're doing, you don't have to watch all those videos. Remember, you're just doing this because you want to. Everything is optional. So the whole point is just to kind of get some exposure to what's going on. So that's my written up way too high thing. And she's 30 degrees off of this direction. So that's TCD. So again, if you're already kind of getting this, go ahead and stop the video, pause the video. Don't stop the video. Pause the video and see how far you can get on your own, and then you can just make sure you got the same answers as me. If you're like, I've never seen this before, this is desperately fascinating, then, good for you. Good to learn things that are desperately fascinating because, stuff. So this way is the force from D to F, D to G, and then this one is a force down from D to E. Okay. And again, sum of the forces in the x direction, minus dgd plus 200 minus 1/2 TCD equals 0. Sum of the forces in the y, and you're like, I just wanted to see the SolidWorks. You know what? Go fast forward. That's what fast forward is for. We're just here to play and learn and stuff. Because you'll watch these videos and they'll be like, clearly blah, and you're like, but that's the one part that I didn't understand. So now we've got that TDF is equal to 0. We've got that tension CD. Well, we already knew what that one was. We can do tension DG. I don't think we already had that one. Tension DG is negative 59.8. And tension DE, we don't already have that one. Tension DE is 450. And we move it over. Beautiful. Look at all these things we're finding. Aren't we super smart? And nobody cares about you anymore. It's a very, very sad life for a minimized thingy that does math. derivation? I don't know. Okay, let's do joint E, because I think we're only missing, so we've got this one, and 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 this one. So if we do joint E, that'll help us finish off what we need. So joint E, she's got tension DE. She's got EX, yay, we get to use that. She's got EY. She's got AE. And she's got this 45-degree tension EG. We'll call her EG. Do we already have EG? No, we don't already have EG. Okay. Now this one is at a 45-degree angle, so that means I can break it out into root 2's over 2's. So she's going to get broken out into root 2 over 2 TEG and root 2 over 2 TEG. Excellent. So I'm going to do the sum of the forces in the x direction. I don't even know what's going on anymore. Do 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 do. Is there a mute button that just gives me the important stuff, but I don't have to listen to her sing? From your lips to heaven's ears, root 2 over 2 TEG plus TDE plus EY equals 0. So TEG equals some number that I have written on this other piece of paper, because why in heaven's name would I do this without having done it first? And then TDE equals some other number, 450. Do I already have that? Feels like I do. I already have that one. What's the one that I'm missing? I think that was the, no, I was missing TAE. TAE is some number 275. Yay! You're like, how did you get that? Check your calculator, I swear. Or maybe I did something goofy with the equation, but I do know the numbers are right. So, more numbers. We are running out of space. Already? Did I already have EG and I just wrote it? No, I didn't. Alright, so there we go. We're throwing that over there because deeply, deeply don't care about where all those stupid numbers are going. Poor little girls, though. They're so teeny weeny. Let's make them bigger so they can be with their friends. Okay, because we've got a little bit more to go. So we have this one and we have this one. Now we've only got one final stupid thing to be done with. So let's look at joint A. So if we look at joint A, we've got a force coming off this way. It's force AE, tension AE. We've got one going this way, which is tension AG, and we've got just AY coming up here. Now tension AG is still at that 45-degree angle, which means we can rewrite it as square root of 2 over 2 in both directions. Root 2 over 2 T tac, root 2 over 2 TG. And the only thing I care about is that TAG, some of the forces in the y direction are AY, root 2 over 2 TAG. That equals 0. TAG equals some other number called negative 389. And we are blessedly, blessedly, blessedly done. And we've got all these goofy numbers. And the question is, could we have done this much, much, much faster in SolidWorks? And the answer is yes. So just to review what you've done all of this algebra, a lot of algebra. You've done a lot of algebra to get a whole lot of numbers. And the idea is that you're just going to every single point, and because of physics, that if a system is in equilibrium, then that means that every subpart of it is in equilibrium as well, which is how we're able to actually go in there and say, oh, well, the sum of all of these are 0, and the sum of all of these are 0, because the only way that this truss can be in equilibrium is if all the individual joints are as well. So the next thing we're going to do is we're going to go take all of this and we're going to plug it into SolidWorks and see if we get mostly the same answers. So we've just started a new part in SolidWorks, so we're going to, I guess, sketch on the front plane. Now we can do all of the sketch at once, which is kind of nice. So I'm going to go pachoo, pachoo, and I'm going to make that 4. No, not that. Smart dimension. 4. And the default is in newtons and meters, so I don't have to worry about any of that. And I can just start drawing the picture. So the picture goes out straight, and then it goes up, and it makes a triangle, and I can hit escape so that it gets off the drawing tool. And I might as well go ahead and smart dimension stuff as I go. No, not that kind of a dimension. So see, this is important. See, this dimension is an uppy-downy, so it's basically a height of the triangle dimension, and that's not what I want. I want a length of the leg dimension. Come here, sweetie. There you go. 4 and 4 and 4. This is very exciting. And I'm going to have this one, and she's going to go straight off to the side. And it didn't actually tell me in the original how much it is, so I'm not going to put that in. So, ooh, not an arc. I'm going to go from here to here, 90 degrees. Then I'm going to add a line from here to here. And that's automatically in the right place, the right distance. And then I'm going to come here. And you see there's that little yellow sign that's like the coincident and the perpendicular. So whenever I click on that, it's still blue, so I'm going to zoom in. I don't know why it does this. So if I pick it up, it lets me move it around. But whenever I take it exactly back to where it was, it's like, oh, that's what you meant. It's fixed now. So that's good. Then we have a line going from here to here, and a line going from here to here. And we care that this angle right here is 90 degrees. Beautiful. So I can exit this sketch. Ooh, it's not fully defined. Why are you not fully defined? Looks like I have a weird thing going on here. What is this? Why is there a dot there? I'm going to delete that. And I'm going to take this one off. So you probably don't have this problem because you probably did it right the first time. But here to here, line, check, exit. Oh, goodness. Is this one of those cases where it's easier just to redo the whole thing? Oh, random thing in there for no reason. Who knew? Doop, doop. Now are you fully defined? Yes. Amazing. Okay, so the next thing I want to do is I'm going to make sure that my Weldments toolbar is on. So go to View, Toolbars, and Weldments. You're going to click the button that says Create a Weldment Feature. And then what we're going to do is we're going to create this whole thing. So click on Sketch 1 and then say Make a Weldment. Now, we have to create a group, so we're just going to start selecting things, and once it stops letting us selecting things, we're just going to create a new group, so it won't let me do any more. So I'll just say New Group, and I'm just going to keep selecting things and clicking New Group until it finally, so New Group, alright, there, and everybody's been selected, so I'm good to go, and if you scroll in, you see we actually have a little welded thingy now, so that's nice. Okay, let's do a study. A static study. Okay, I always forget to do this, so I'm going to right click and apply my favorite material, which is always plain carbon steel, because that's how I like to do things. Fix geometry. I'm going to fix this joint over here, perfectly fixed because it was a pin joint. And then over here, I'm going to not exactly fix these because he was on a roller. So I'm going to use reference geometry, click a point, click some kind of a plane thingy, except that's not the direction I want the translation to be had. Delete. So I actually want the translation to be limited in the uppy-downy direction. So there's my uppy-downy arrow, says you can't go that way anymore. I'm like, yay, thank you. All right, now I need a force up here, so an external load. Make sure I'm on a point. Point. Now I need a reference geometry, so I'm going to go up, down. And the up, down is going to be 300. Let's check and see. Wrong direction. Like that. Good. And then over here, I want another force. It's a pin thingy. And select a line. So it's along that line. And it's a 200 Newton force. And it's the correct direction, which is amazing because that pretty much never happens. All right, I'm in good shape. Now I'm going to run the study. Okay, the study has been run. All right. And this deformed result just looks silly, so I'm going to take that out. Now, if I look at the resultant forces, so those would be my two down here, the equivalent of the A and the E. So whenever I look at those guys, I'll see that I got 274 instead of 275, which is beautiful. Here I got negative 200, which is exactly right, and then 25.6, I got 25, so you know, the percent difference on that is still very, very small, so I'm perfectly happy with leaving that the way it is. then I can go and I can actually look at the individual beam forces. So if you're not paying attention, you're not going to see, because for some reason it just pops that thing up in there and it looks weird. So we just say, yeah, I want to see the beam forces. Okay, and it gives you all this data, which is all the exact same thing, and I think that has to do with the number of iterations that it's looking at. So I just want to see the extreme values. Okay, and I've tried renaming this, so if anybody has a good idea on how to rename the structure so that it shows up as the beam names up here, please place a comment and let me know, because that's something that's been driving me nuts. But in any case, if I click on it and I look up here, I can say, okay, so this was my beam from C to D. And if I go look at my answers, I had that B from C to D was 520. And in fact, I've got 521, which isn't exactly right or perfect, but it's a numerical solution. So we don't expect an absolutely perfect answer. Now you may freak out and say, but this is a negative number and we had a positive number. That just means they're using a different convention. So we drew our arrows going out from the point. They drew their arrows going into the point. So really the only thing you want to make sure is that all of their answers are backwards, or the opposite of what you got. So we want to make sure that all of our answers are 100% backwards. All right, so the second structural member is this guy over here, and that was GE. And if we look at EG, negative 672, and so positive 674, which is just perfectly fine. This one down here was AE. AE we had was 275, and we've got negative 275-ish. This one over here was DG. DG we had was negative 59. They got positive 60. So see, isn't this amazing, and how much faster this was in the 20 minutes it took us to do this earlier? So CG is negative 520. They got positive 520. This guy over here was DE, which we got positive 450. They're at negative 450. Now this one here is actually our zero force member. They got a entirely non-zero force, or not entirely zero force, but you know, it's basically as perfect as we care about. And then this guy was AG. AG we got negative 389, and they got positive 390. Got two more to check. We're just checking them all, even though I'm pretty much a believer now that SolidWorks can do basic functions that I learned how to do in statics. CD is 520, and they got negative 520. And finally, BG, we got negative 600, and they got positive 600. So this is really kind of cool that you can get and confirm the same answers that you're getting on pencil and paper with what you're getting in SolidWorks. Also gives you a little bit of time to play around and get a feel for what it's like to do finite element analysis.